Well, hopefully on both Zoom and Panopto, things are working and we are ready for this online review session. The problems that I am planning to cover, maybe I'll get through all of them, maybe not. These are questions that you sent in. Page 433, 21 through 29, 472, you can see the problems. And again, I will attempt to go through these in order, so if you want to jump around the video, absolutely no problem. So, first page of notes. We're looking at the problems on page 433. Numbers 21 through 29. So in 21 through 29, we want to basically find a formula for 2 cosine of 5 theta. Well, but to do that, first again, like we've done in several other problems, we're going to use de Moivre's theorem to get a formula for cosine of 5 theta. So we know that if you take CIS theta and raise it to the 5th power, you multiply the angle by 5. But the binomial theorem says you can expand this out. The old a plus b to the 5th power is a to the 5th plus 5a to the 4th b, and so on and so on. So again, what we'll do is we'll expand this out. Keep in mind this is cosine of 5 theta plus I times the sine of 5 theta, meaning we're going to compare the real parts of both. So this is going to be a real part and a complex part, and I'm going to want to compare the real parts. So this is going to be cosine to the 5th power. Then it's going to be 5 cosine to the 4th times I sine to the 1st. Well, that's going to belong to the I part. We're really not interested in that. Let me do a quick little, let's see. So this is 5 choose 0. This is 5 choose 1. This is going to be 5 choose 2. Well, 5 choose 2 is 10. So this is going to be 10 cosine cubed sine squared. The next term is going to be complex. The next one that's going to be purely real is going to be cosine to the theta sine to the 4th of theta. Well, how many? Well, this is going to be 5 choose 1. So again, binomial theorem says it's cosine to the 5th. Then there's one that has a cosine to the 4th, but there's going to be an I in front. 10 cosine cubed sine squared. 5 cosine sine to the 4th. Again, we ignore the parts that are purely complex. And what we come up with is that the cosine of 5 theta is cosine to the 5th of theta plus 10 cosine cubed 1 sine squared. But sine squared we're going to replace by 1 minus cosine squared. Plus 5 cosine theta. This is sine squared squared. So it's 1 minus cosine squared squared. And now I'm going to have to clean up all this stuff here. So when I clean up all this stuff, let's clean all this stuff up. We're going to get a cosine to the 5th plus we had 10 cosine cubed times 1 minus cosine squared. So that's going to be plus 10 cosine cubed minus 10 cosine to the 5th plus 5 cosine 1 minus cosine squared squared. Well, squaring this out, you get 1 minus 2 cosine squared plus cosine to the 4th. Multiplying by 5 cosine, let's see, there was the 1 plus 5 cosine of theta. From here, there's going to be a 2 cosine squared, but multiplied by this, it's plus 10 cosine cubed. Here we're going to get a cosine to the 4th times this is 5 cosine squared, rather times 5 cosine to the 5th. Now, let's combine the various like terms here. We get 1 cosine to the 5th minus 10 cosine to the 5th and 5 cosine to the 5th. So that seems to give us a total of negative 4 cosine to the 5th. Let me double check. Important thing. Shame on me. The sine squared, this was actually I times the sine squared. So this came equipped with a negative sign. Again, this actually should be a negative because it's cosine cubed. The I sign was squared. That's a negative. Here it's an ordinary sign, I times sine to the 4th. So that's just a plus 1. So these signs need to be reversed. So now let's collect. We get cosine of 5 theta is equal to 1 cosine to the 5th plus 10 more is 11 plus 5 more is 16 cosine to the 5th of theta. So we've accounted for these. For the cosine cubed, we get, again, let's make sure I'm counting these correctly, plus 10 here and minus 10 here. So they're gone. I actually kind of question that. So again, let me check my arithmetic again. For the cosine cubed, cosine to the 5th, cosine cubed is just going to be minus 10 from here. Cosine cubed is going to be plus 10 copies there. That seems kind of surprising that that cancels out. So these cancel out, and I get plus 5 cosine of theta. Now, since I'm actually interested in a formula in this problem for 2 times the cosine of 5 theta, apparently the cosine cube term doesn't cancel out, so I really have to go back here and check my algebra. Let's go back and check the algebra. For the algebra, what we have is cosine theta plus I sine of theta to the 5th power. So again, looking at a little Pascal's triangle, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and 1, 5, 10, 10, 5, and 1. So we get 1 copy of cosine to the 5th. We get 10 copies of cosine cubed I sine squared, so that becomes minus 10 copies of cosine cubed sine squared. We're going to get 5 copies of cosine to the 1st, I sine to the 4th. Well, I to the 4th is 1, so that's sine to the 4th. Now we replace cosine to the 5th is fine. This becomes minus 10 cosine cubed, 1 minus cosine squared, plus 5 copies of cosine times sine to the 4th. Well, this is a sine squared squared. Let's collect my algebra again. I've got my cosine to the 5th. This thing expanded out as minus 10 cosine cubed plus 10 cosine to the 5th. This one expands out as, this one in particular was 1 minus 2 cosine squared plus cosine to the 4th. So when I multiply out, I get 5 cosine theta minus 10. Let's see. I get plus 5 cosine theta minus 10. Minus 10 cosine cubed plus 5 cosine to the 4th. Now when I collect the terms, the cosine to the 5th is 1 copy here, 10 copies here, 5 copies there. There's 16. For the cosine cubed, this is much better. Minus 20 cosine cubed. Always easy to make mistakes the first time around. And then plus 5 cosine of theta. Now, the problem asks for a formula for 2 cosine of 5 theta. So 2 cosine of 5 theta is 32 cosine to the 5th minus 40 cosine cubed plus 10 cosine theta. Well, if you look at this, this is 2 cosine of theta to the 5th power, because 2 to the 5th is 32. If I look at 2 cosine of theta cubed, that gives me 8 cosine cubed. To get to the minus 40, I need another minus 5. And if I look at 2 cosine of theta, the plus 10 means I have 5 copies of this. So lo and behold, I have the formula 2 cosine of 5 theta is 2 cosine of theta to the 5th minus 5 2 cosine of theta cubed plus 5 times 2 cosine of theta. So that's what we have here. And if we look at the formula on the book on page 433, that is in fact precisely the formula that we're looking for. So we've got this formula in the bank, and now we're supposed to figure out in the next exercises, show that 2 cosine of 18 degrees is a root of, we want 2 cosine of 18 is a root of x to the 4th minus 5x to the 5th plus 5. Well, if we take this formula, 2 cosine of 5 theta equals 2 cosine of theta to the 5th minus 5 2 cosine of theta cubed plus 5 2 cosine of theta. If we let theta equal 18 degrees, we get 2 cosine of 90 degrees, which by the way, cosine of 90 is 0, so this is going to be 0, is 2 cosine of 18 degrees to the 5th minus 5 2 cosine of 18 degrees cubed plus 5 cosine of 18 degrees. And lo and behold, 2 cosine of 18 degrees gives you 0 when you plug it into x to the, what am I writing here? X to the 4th minus 5x squared. So this is the polynomial x to the 5th. In other words, you've plugged 2 cosine of theta into x to the 5th minus 5x cubed plus 5x. So here's what we've shown. 2 cosine of 18 degrees, when you plug it in here, is a root of something to the 5th minus 5 times something cubed plus 5 times something. So 2 cosine of 18 degrees is a root of this. But notice, this is x times x to the 4th minus 5x squared plus 5. Notice you could factor an x out. Well, 2 cosine of 18 degrees isn't 0. So since 2 cosine of 18 degrees isn't 0, it's actually a root of this polynomial. Because again, we show that 2 cosine of 18 degrees is a root of this. But this is equal to x times x to the 4th minus 5x squared plus 5. Let me see if I can get the focus to be a little bit better here. I hope that helps. So notice 2 cosine of 18 degrees is a root of this polynomial, which is a product of these 2 polynomials. But 2 cosine of 18 degrees doesn't make this equal to 0. Doesn't make this equal to 0, because 2 cosine of 18 degrees is not 0. So 2 cosine of 18 degrees has to make this one equal to 0. So therefore, 2 cosine of 18 degrees is a root of this polynomial. Well, what we did is we solved this problem by plugging theta equals 18 degrees into this polynomial. Well, for the rest of this, you can then say, well, if I plug in 54 degrees or 126 degrees or 162 degrees, it's always going to make this one equal to 0. So plugging in 18 degrees gave you a root of this. And the same thing happens if you plug in, let's see, the choice is 54 degrees, 126 degrees, and 162 degrees. So that takes care of problem number 23. Now, if we want the exact value of cosine of 18 degrees and the exact value of the cosine of 54 degrees, notice all you're doing is you're looking for the roots of this particular polynomial. Well, let's look at the roots of this particular polynomial. We have x to the fourth. Let's put this where you can see it. X to the fourth minus 5x squared plus 5. Well, if you let t equal x squared, this is t squared minus 5t plus 5. Quadratic formula says that t equals 5 plus or minus the square root of 5 squared, 25, minus 4 times 5, so that's 25 minus 20 over 2, or t is equal to 5 plus or minus 2 times the square root of 5 over 2. Which means x is, now if you notice, 2 times the square root of 5 is less than 5. So even if I subtract, this is positive. So both values of t are positive. So that means you can take square roots of both of these, and x is plus or minus the square root of 5 plus 2 square root of 5 over 2. So the 4 roots of this polynomial are plus or minus the square root of 5 plus 2 root 5 over 2. Now, if you look at these, 2 of these roots are positive and 2 of these roots are negative. Well, if you're looking for cosine of 18 and cosine of 54, well, actually, cosine of 18 degrees and cosine of 54 degrees are both positive. So the 2 positive roots of these represent 2 cosine of 18 degrees and 2 cosine of 54 degrees. Because again, this polynomial had 2 positive roots and 2 negative roots. Well, since 2 cosine of 18 and 2 cosine of 54 are both roots and they're both positive, 2 cosine of 18 degrees and 2 cosine of 54 degrees are equal to this. Now the question is which is which? Well, if you think about cosine in the first quadrant, again, there should be plus and minuses here. Cosine in the first quadrant is decreasing. So cosine of 18 degrees is the larger one. Cosine of 54 degrees is the smaller one. So 2 cosine of 18 degrees is the larger one. So that's 5 plus 2 root 5 over 2. And 2 cosine of 54 degrees has to be the smaller. So square root of 5 minus 2 square root of 5 over 2. Because again, these are the 2 positive roots of this polynomial. So 2 cosine of 18 degrees and 2 cosine of 54 degrees are these 2 values. Well, which one is which? 2 cosine of 18 degrees is the bigger one. If you think about the graph of the cosine, 2 cosine of 15 degrees is the smaller one. Now, if you're looking for a monic irreducible polynomial that has cosine of 18 degrees and cosine of 54 as 2 of its roots, well, let's see. Our good friend, x to the fourth minus 5x squared plus 5 has as its roots, so again, now we're moving to number 25. This has as 2 of its roots 2 cosine of 18 degrees and 2 cosine of 54 degrees. Now, if this polynomial has these as roots, what would have cosine of 18 degrees and cosine of 54 degrees as roots? Well, again, here's what we can play with. We know that 2 cosine of 18 degrees to the fourth minus 5, 2 cosine of 18 degrees squared, plus 5 is equal to 0. That means 16 cosine to the fourth of 18 degrees minus 20 cosine squared of 18 degrees plus 5 is equal to 0. That means cosine of 18 degrees is a root of 16 x to the fourth minus 20 x squared plus 5. So both cosine of 18 degrees and cosine of 54 degrees are roots of this polynomial. And if we're looking for a monic irreducible polynomial, you just divide everything by 16. And here is a monic irreducible polynomial with coefficients in Q that has cosine of 18 degrees and cosine of 54 as its roots. Again, the way that I got it was 2 cosine of 18 degrees and 2 cosine of 54 degrees are roots of this. If you plug it in, this is what it tells you. And that says cosine of 18 degrees and also cosine of 54 degrees would be roots of 16x to the fourth minus 20x squared plus 5, and I can make this monic. Well, how do we know this is irreducible? Well, the only difference between this polynomial and this polynomial is multiplying or dividing by 16. So if I want this one to be irreducible, it's the same as this one being irreducible. But notice for this one, you can use Eisenstein's criteria with p equal to 5, because 5 divides both of these, 5 doesn't divide this, and 5 squared doesn't divide this. So this is irreducible by Eisenstein's criteria using the prime, p equals 5. So that actually takes care of 21 through 25. Similarly, let's move on to 26 through 29. In 26 through 29, we had already derived the formula. It refers back to 14. 2 cosine of 4 theta is equal to 2 cosine of theta to the fourth minus 4 times 2 cosine of theta squared plus 2. So if you plug in 22.5 degrees, so again, this was obtained from problem 14. If you plug in 22.5 degrees, you get 2 cosine of 90 degrees. Once again, we get 0. So we get 2 cosine 22.5 degrees to the fourth minus 4, 2 cosine 22.5 degrees squared plus 2. Or in other words, what equals 0 was when we plug cosine of 22.5 degrees into the polynomial, x to the fourth minus 4x squared plus 2. In other words, this polynomial has 2 cosine 22.5 degrees as a root. Because again, you can see 2 cosine of 22.5 degrees is a root of x to the fourth minus 4x squared plus 2. So there's a monic polynomial of degree 4 in z of x that has 2 cosine 22.5 degrees as a root. So that takes care of number 26. For 27, we want to show that this is irreducible. Well, notice Eisenstein with p equal to 2. This is divisible by 2. This is divisible by 2. This is not divisible by 2. This is not divisible by 4. So this is irreducible. Eisenstein's criteria, p equal 2. number 28, show that the other roots of this polynomial are 2 cosine of 67.5, 2 cosine of 112.5, and 2 cosine of 157.5. Well, the point is, if you plug in all those values for theta, again, 67.5 degrees, 112.5 degrees, 157.5 degrees, they're all going to make this equal to 0. So just the way cosine, just the way the 22.5 degrees worked in here, you can plug in any of the other ones. And now the final part of the problem is it's asking for the exact values of cosine of 22.5 degrees and cosine of 67.5 degrees. Well, here's the story. By the way, let me just go back for the previous ones. Again, what I had done in a previous problem, I had found the values of 2 cosine of 18, 2 cosine of 54. What I'll do here is I'll find the exact values of 2 cosine of 22.5 degrees and 2 cosine of 67.5 degrees. And that'll be good enough, because then you can just divide by 2. So in other words, I'm looking at this polynomial. And again, 2 of its roots are going to be 2 cosine of 22.5 degrees and 2 cosine of 67.5 degrees. So 2 of the roots of this polynomial are going to be 2 cosine of 22.5 degrees. And again, looks like the focus isn't quite what I want it to be. And 2 cosine 67.5 degrees. So how do we get the roots of this? Well, we let t equal x squared. So we get t squared minus 4t plus 2. Quadratic formula says t is equal to 4 plus or minus the square root of 16 minus 8. Again, 16 minus 8. The whole thing over 2. So t is 2 plus or minus square root of 8 is 2 root 2 divided by 2. So notice 2 is bigger than the square root of 2, so both of these are positive, so I can take square roots. So x is plus or minus the square root of 2 plus or minus the square root of 2. So these are the 4 roots of this polynomial. Notice 2 are positive and 2 are negative. So 2 cosine of 22.5 degrees and 2 cosine of 67.5 degrees are both positive. So they are the 2 positive roots. So here's one positive root of this polynomial. Here's the other positive root of this polynomial. This is clearly the bigger one. This is clearly the smaller one. In the first quadrant, the cosine decreases. So 2 cosine of 22.5 degrees is equal to this, because that's the bigger one. And 2 cosine of 67.5 degrees is the other one. Again, the problem asks us to find cosine of 22.5 degrees and cosine of 67.5 degrees. Well, so all you have to do is just take these answers and divide by 2. So the moral of the story in these problems is, using de Moivre's theorem, you can get an awful lot of nice formulas for the cosine, and that can enable you by hand to compute the exact values of certain cosine function points. I said that badly, but the point is, de Moivre's theorem allows you to by hand compute some exact values of the cosine. So that takes care of the stuff on page 433. Let me now move to the stuff on page 472. Page 472, the first problem that was requested was 29. In 29, we're trying to find the minimum polynomial for root 3 plus root 5 over q. So first, let's find something. So suppose alpha equals root 3 plus root 5. There are 2 radicals there. That's more than I want. If I square, I should be able to get rid of 1. So alpha squared is 3 plus 5. plus 2 times the square root of 15. Now we only have one radical left. Now alpha squared minus 8 is 2 root 15. If I square both sides, alpha to the 4th minus 16 alpha squared plus 64 is equal to 4 times 15, or alpha to the 4th minus 16 alpha squared plus 4 is equal to 0. In other words, root 3 plus root 5 is a root of x to the 4th minus 16 x squared plus 4. So this is a polynomial with coefficients in Q satisfied by root 3 plus root 5. Now, this will be the minimum polynomial if and only if it's irreducible in Q. Well, you could, I mean, this clearly doesn't have any rational roots. In fact, the way that I'll show this is irreducible is the roots of this polynomial are plus or minus root 3 plus or minus root 5. Because you can check that this is an even function. So if one thing is a root, so is its negative. But if you check these calculations, if I had to replace this by a negative sign, it would also work. So it's easy to see that since this is an even function and replacing this by a negative sign, it also works. All 4 of these things are roots. Well, for shorthand, let me call these 4 roots alpha 1, alpha 2, alpha 3, alpha 4. That means this polynomial factors as x minus alpha 1, x minus alpha 2, x minus alpha 3, x minus alpha 4. So this polynomial factors as x minus alpha 1, x minus alpha 2, x minus alpha 3, x minus alpha 4, where alpha 1 through alpha 4 are these 4 roots. Well, this thing clearly has no rational roots. You could look at these things and say they're not rational, or you could apply the rational root test. So the only way this could be reducible over Q is quadratic times quadratic. So quadratic times quadratic. But that would say that when you factor these 2 quadratics, you get these 4 terms. Because unique factorization says when you factor this into linear terms, this is the only way you can do it. So if this was reducible in QX, it would have to factor as quadratic times quadratic. And these quadratics would split. This would split into 2 of these, and this would split into 2 of these. But if you take a look at it, whenever you multiply any 2 of these, you're going to end up with square roots of 3s and square roots of 5. I won't write out all the possibilities, but you can check that if you ever multiply 2 of these things, a root 3 or a root 5 is going to survive. Well, that wouldn't give you rational coefficients. So in other words, you can't factor this polynomial into 2 quadratics with rational coefficients because they would each split into 2 of these, but when you multiply 2 of these, you don't get rational coefficients. So this has root 3 plus root 5 as a root of it, and this is irreducible over Q, so there's your minimum polynomial. So that's number 29 from this section. Next one from this section that you requested was 37. For 37, we're looking for the minimum polynomial over this field, not over Q, but over this field. And in number 37, we want the minimum polynomial for root 3 plus root 5. And here's the story. You start off with the same exact computations here, and you get this polynomial. And then you ask the question, is this polynomial irreducible over this field? Well, it comes down to the same thing as before. If this factored over Q root 2x, it would factor into these 4 pieces. So if this factored into quadratics, these quadratics would factor into these 4 pieces. But again, just as before, when you multiply things of this form together, you're always going to get root 3s and root 5s. but this field doesn't contain root 3 and root 5. Again, we could go through more work to do it, but the point is the square root of 3 does not live in here. The square root of 5 does not live in here. So if this factored into quadratics, the quadratics would then factor into linears, but whenever you glue two of these linears together, your polynomial is going to have root 3s and root 5s in them. They don't live in here. So in fact, the answer to number 37 is identical to the answer to number 29. That's your minimum polynomial over Q. Now, next one from this section is 38. And now we're looking for the minimum polynomial over this particular field of 5 root 2 minus 7I root 3. So now here's the point. If you're looking for the minimum polynomial with coefficients in here, this is not a bad guy because this lives in here. I don't need to do anything to get rid of this. It's the 7I root 3 I need to get rid of. So similar computations, I'm going to let alpha equal 5 square root of 2 minus 7I root 3. And this lives in the field. Something like this is perfectly acceptable to be a coefficient. That's the one I want to get rid of. I want to get rid of this, so I'm going to isolate it. So alpha minus 5 square root of 2 is minus 7I root 3. If I square both sides, I get alpha squared minus 10 root 2 alpha plus, let's see, squaring this, 25 times 2 is 50. Let's see, so you get alpha squared minus 2 times this plus that squared is, let's see, this. Minus 7 squared is 49. 49 times 3, I think, is 147. I squared is negative 1. I think I get minus 147. I hope I did the arithmetic right. Adding 147 to both sides gives me, sorry, that's an alpha squared. Alpha squared minus 10 square root of 2 alpha plus 197. In other words, let's look at the polynomial x squared minus 10 root 2x plus 197. So here's what we know. This is a polynomial of degree 2. It has 5 root 2 minus 7I root 3 as a root. The coefficients are in here, so this is certainly a polynomial with coefficients in here that has this as a root. The only thing we need to do is check that this is irreducible in here. Well, the point is, the two roots of this polynomial are this and its complex conjugate. Neither of these things live in the real numbers, so neither of these things live in the field Q root 2. So this is a quadratic polynomial with coefficients in here that has no roots in here. So this polynomial is irreducible in here because it's quadratic with no roots in here. So the minimum polynomial for this over Q would have degree 4, but the minimum polynomial for this over Q root 2 is just degree 2. Again, we don't need to get rid of 5 root 2 because root 2 is allowed as a coefficient. So the only thing we needed to do was to square this to get rid of the I root 3. So there's your minimum polynomial. And the last problem from this section that was requested was number 43. So number 43 is asking for the minimum polynomial of, once again, good old root 3 plus root 5, but now over the field Qi, and it's the same exact reasoning as we did before, namely, this is a polynomial with coefficients, in fact in here, which has root 3 plus root 5 as one of its roots. This will be your answer if this is irreducible, but the same reasoning here is this factors into 4 pieces. The 4 roots are plus or minus root 3 plus or minus root 5. If you ever think that this could be factored into 2 quadratics, well, each of these quadratics would split this way. Whenever you glue 2 of these things together, you're going to have root 3s and root 5s popping up, but you could check that this field doesn't have root 3, and this field doesn't have root 5 in it. In other words, the answer to this problem is the same as the answer to number 29. So this turns out to be the minimum polynomial for this particular number over q, over qi, over q root 2. And the reason being, whether you look at q or q root 2 or qi, the square root of 3 does not belong to any of these fields. The square root of 5 does not belong to any of these fields, which means x to the 4th minus 16x squared plus 4 was the minimum polynomial for this over each of these fields. Now, if you wanted the minimum polynomial over q root 3, that would only be degree 2, because you allow coefficients in q root 3 in here. Similarly, if you wanted the minimum polynomial over q root 5, that would also have degree 2. Just to illustrate, if you wanted the minimum polynomial over this field, alpha equals root 3 plus root 5, root 3 is okay. So alpha minus root 3 is root 5. Squaring both sides, you get alpha squared minus 2 alpha root 3 plus 3 is equal to 5, or alpha squared minus 2 root 3 alpha, that's a better way to write this, subtracting 5 from both sides, minus 2 is equal to 0. In other words, if you wanted the minimum polynomial over this field, it would be x squared minus 2 root 3x minus 2. And similarly, if you wanted the minimum polynomial over this field, it would be a slightly different quadratic. But since none of these particular fields contain root 3 and none of these particular fields contain root 5, this turns out to be the minimum polynomial for root 3 plus root 5 over all of these fields. It's not until you get to fields like this that the minimum polynomial has smaller degree. Just as if you wanted the minimum polynomial over the reals, it would just be x minus root 3 plus root 5, because root 3 plus root 5 is a real number. So that takes care of the problems from page 472. Let's now move to the list of problems from page 490. Sorry, 590. So on page 590, first question was, the situation that we're really looking at is fields in between the rational numbers and q root 7, root 5 to the 1/3. So we're really looking at fields between q and up here q square root of 7 and 5 to the 1/3. So this is the smallest field that contains the rational numbers and 5 to the 1/3. The way that you could get to it is two ways. You could first tack on the square root of 7 and then tack on 5 to the 1/3. Or you could first tack on 5 to the 1/3 and then tack on the square root of 7. To fill in some things that weren't asked about, this degree is 2 because the square root of 7 satisfies the polynomial x squared minus 7. That's irreducible over q, degree 2. If we want this degree, well, 5 to the 1/3 satisfies xq minus 5. It's irreducible with coefficients in q, so this is 3. Now, if we go up this way, 5 to the 1/3 satisfies a polynomial of degree 3 with coefficients in q. So it certainly satisfies a polynomial of degree 3 with coefficients in here. So this one would be at most 3. In the same way, this would be at most 2. So the answer here is at most 6. But it's divisible by 2 and 3. Since 2 and 3 are relatively prime, this says this is actually a multiple of 6. Well, if this is at most 6 and a multiple of 6, this big extension is 3, rather is 6. And now we can fill in, this degree is this times this, so this degree has to be 3. This degree is this times this, so this degree has to be 2. And we get the cute little picture that actually solves pretty much problems 1 through 5. But what was asked was 7 and 8. 7 says, if you take something in Q root 7 and it's not in Q, find Q root 7 over Q alpha. Well, let's just draw a little story here. Here's Q. Here's Q, the square root of 7. And you're taking some alpha which isn't in Q, and you're looking at the field in the middle. Well, this degree is equal to 2. So that means this degree times this degree is equal to 2. So one of these is 1, and one of these is 2. But we're told that alpha isn't in Q, which means these fields are not the same. Again, if you have 2 fields and the degree of one over the other is equal to 1, that means they're the same field. Since alpha is not in Q, this is not equal to 2. So this has to be 2. And since this times this has to be 2, this has to be 1. So in fact, this says if you take any alpha that's not in Q, you get all of Q root 7. So this is equal to 1. Similarly, almost the same exact problem. I'll put the picture over here. Here's Q. Here's Q 5 to the 1/3. And this dimension is equal to 3. Well, suppose somewhere in the middle we have Q beta. That means this degree times this degree is equal to 3. So one of these is going to be 1, and the other one is going to be 3. Well, if it's equal to 1, that means that the fields are the same. So either these fields are the same, or these fields are the same. But we're told that beta is not in Q. So these fields are not the same. So if one of these is 1 and one of these is 3, this has to be 3, and this has to be 1. In other words, when you look at Q 5 to the 1/3 over Q beta, that in fact has to equal 1. So if you took any element in this field that wasn't in Q, it actually gives you this entire field. Because again, one of these is going to be 1, one of these is going to be 3, but if beta is not in Q, these fields are different, it has to be 3. So that takes care of 27 and 28. Rather, that takes care of 7 and 8. Let's move to 27 is the next question. In 27, it's saying, find some beta in Q 14 to the 1/4, if I'm reading that correctly. Let's check again. That looks like 14 to the 1/4. That it gives you a field extension of degree 2. Now, here's what we know. If you took Q 14 to the 1/4 over Q, that would be equal to, well, the minimum polynomial of 14 to the 1/4 over Q is x to the 4th minus 14. Sorry. Since this is irreducible degree 4, this extension is 4. So here's Q 14 to the 1/4, and this entire extension is of degree 4. We want to find something that makes this equal to 2. Well, here are some things we know. If we look for a basis of this extension, a basis is 1, 14 to the 1/4, 14 to the 2/4, or the square root of 14, and 14 to the 3/4. So this is a basis for this field extension over Q. But if I think about this particular element, 14 to the 1/2, it satisfies the polynomial x squared minus 14. So in other words, if beta was 14 to the 1/2, this would give me an extension of degree 2 because beta satisfies the polynomial x squared minus 14. So in other words, the minimum polynomial for 14 to the 1/4 over q is this. But the minimum polynomial for 14 to the 1/2 over q is equal to this. So 14 to the 1/2 gives me a field extension of degree 2. Now, there are other numbers that you could deal with, but they would all somehow involve 14 to the 1/2. So there are other answers, but probably the easiest answer is 14 to the 1/2. So that takes care of number 27. Let's move along here. Page 13 of the notes. The next problem that someone asked about was 35, and in fact there are a whole bunch of things related to. We're looking at the big field we have on top is q 2 to the 1/6, 2 to the 1/10. So 2 to the 1/6, 2 to the 1/10. The bottom field is q, and along the way we could tack on q 2 to the 1/6. Here we could tack on q 2 to the 1/10. So in other words, we could break this into pieces. Now, 2 to the 1/10 is a root of x to the 10th minus 2. That's irreducible. That means this is degree 10. 2 to the 1/6 is a root of x to the 6th minus 2. So this is degree 6. That means, again, if you threw 2 to the 1/10 onto this, you would get at most 10, because x to the 10th minus 2 is a polynomial with coefficients in here that has 2 to the 1/10 as a root, but x to the 10th minus 2 might not be irreducible here. So this one is at most 10. In the same way, this one is at most 6. That means the big extension here is at most 60. It might not be all of 60. Again, these things are not relatively prime. So since this is divisible by both 6 and 10, that might not make it all of 60. It says if you're divisible by 6 and 10, then you're divisible by 30. So this could conceivably be 30. It could conceivably be 60. But let's keep playing. So the first part that was asked was 35, and that says you have to show that q 2 to the 1/6, 2 to the 1/10. In other words, this is the smallest field that contains 2 to the 1/6 and 2 to the 1/10. We have to show that it's the same as 2 to the 1/30. So let's go to a new piece of paper. And what we are trying to compare is q 2 to the 1/6, 2 to the 1/10, and we want to compare it to 2 to the 1/30. So what we need to show is if this field contained both 2 to the 1/6 and 2 to the 1/10, then this field would live in this field. If this field contained 2 to the 1/30, then this field would be contained in this field. So we need to show that both of these live in here, and we need to show that this lives in here. So if you think about 2 to the 1/6, what is its relationship to 2 to the 1/30? Well, if you raise 2 to the 1/30 to the 5th power, you get 2 to the 1/6. So this field contains 2 to the 1/30. So this field contains 2 to the 1/30 raised to the 5th power. So this field contains 2 to the 1/6. So 2 to the 1/6 lives in here. Similarly, what's the relationship between 2 to the 1/10 and 2 2 to the 1 over 30? Well, if you raise 2 to the 1 over 30 to the third power, you get 2 to the 1/10. So 2 to the 1 over 30 lives in here. 2 to the 1 over 30 cubed lives in here. That means 2 to the 1/10 lives in here. So this is the smallest field that contains 2 to the 1/6 and 2 to the 1/10. But they both live in here. So everything in this field lives in here. So that's one direction. And the other direction is, how do we get 2 to the 1 over 30 in here? Well, so how do we get 2 to the 130 in here? Well, if we think about it, here's the question. Can you write 2 to the 130 as 2 to the 1/6 raised to some power, so this is a question mark, times 2 to the 1/10 raised to some power? Because again, this field contains 2 to the 1/6 to any power times 2 to the 1/10 times any power. Does that force 2 to the 1/30th in here? Well, this would be true if 2 to the 1 over 30 was 2 to the a over 6 plus b over 10. So that then says, again, still question marks, can I write 1 over 30 as a over 6 plus b over 10? Well, multiplying both sides by 30, that's the same as saying, can I write 1 as 5a plus 3b? Well, since 5 and 3 are relatively prime, I can certainly do that. In fact, if I just kind of stare at it, a equals -1 and b equals 2 will do the trick. So in fact, 2 to the 1 over 30 is 2 to the 1/6 to the -1 power times 2 to the 1 over 10 to the second power. Well, 2 to the 1 over 6 to the -1 times 2 to the 1 over 10 squared lives in here. In other words, 2 to the 1 over 30 lives in here. Well, if this is the smallest field that contains q and 2 to the 130, and so does this is contained in that. In other words, these two fields are equal to each other, which in fact solves the whole story of, since this is the same as just tacking on 2 to the 1 over 30, and the minimum polynomial for 2 to the 1 over 30 over q is x to the 30 minus 2. That means this degree is actually equal to 30. So not only was this one at most 10, it turned out that it was 5, because this product had to be 30. And not only did this one have to be at most 6, but it actually turned out to equal 3, because this times this is equal to 3. So the first problem from this set that one wondered about was problem 35, and I think we just succeeded in showing that these two fields are the same. Next problem from this set was 39, and check if this dimension, 2 to the 1/6, the dimension of 2 to the 1/6, 2 to the 1/10 over 2 to the 1/6, see if that is equal to this dimension. So again, 39 is saying, is this degree equal to this degree? And the answer was no. This was 10 and this was 5. So that's what 39 was asking about. And 43 was asking to compute the degree of this over, let me read carefully, 2 to the 1/2. Well, let's think about this. I'll draw another little picture for you. The big field that we're talking about, we just showed that that was the same as q 2 to the 1 over 30. And here's the bottom field, q, and we know that this big degree is equal to 30. Now what problem 43 is talking about is, where does q 2 to the 1/2 live in all this? Again, notice 2 to the 1/2 does live in here, because if you raise 2 to the 130 to the 15th power, you get 2 to the 1/2. So what problem 43 is asking about is, what's this degree? Well, this degree is equal to 30, and it's this degree times this degree. But here you're just looking for the degree of 2 to the 1/2 over q. Well, 2 to the 1/2 satisfies x squared minus 2. That means this degree is equal to 2. Well, if this times this is equal to 30, and this is equal to 2, this degree has to be 15. So the answer to number 43 is 15, because the big degree is 30, this little degree is 2, so then the one in the middle is 15. So that takes care of problem number 43. Okay. The next set of problems seem to be a big bunch. It's 63, 65, 67, 69. And so the story is, the little field down here is Q, and the big field on top is Q, root 2, root 3, and I. So this is the smallest field that contains the square root of 2 and the square root of 3 and I. And what 63 is asking for is 63 is asking for this degree and well, not over Q, but over Q. I'll write this over again. Okay. So 63 is asking for these two. Well, if we're looking for the degree of q I root 2 over q, we have to say what's the minimum polynomial for I root 2 over q, and that would be x squared plus 2. This is certainly irreducible over q. It has I root 2 as a root, so this degree is 2. Now, for the second part of the problem, instead of looking at the whole big picture, I'll just take this little picture here. Here's q. Here's q root 2i. So this is the smallest field that contains the rational numbers, the square root of 2, and I. Let me break this into little pieces. This is q root 2. This is qi. And the easiest way to look at this is when you go from q to q root 2, root 2 is a root of x squared minus 2, which is irreducible over 2. So this is 2. When we go from here to here, we're taking this field and we're also throwing in I. Well, I satisfies the polynomial x squared plus 1. So if x squared plus 1 is irreducible over q root 2, this will be 2. If x squared plus 1 is reducible over q root 2, this will be 1. But none of the roots of x squared plus 1 are real numbers. This field just contains real numbers. In other words, x squared plus 1 has no roots in q root 2, so x squared plus 1 is irreducible over q root 2. So this really is equal to 2. So this is equal to 4. So the extension q root 2 comma I over q has degree 4. Now, sitting in between these two is q root 2i. Put a little dot here to represent that one. This one will be q root 2i. Well, this whole thing is equal to 4. Okay. And if you're wondering what the degree of q root 2i over q is, well, we already determined that that was equal to 2. Again, the degree of q root 2i over q, that's exactly what we determined before. So this is 2. Well, if this product is 4, this has to be 2. So the degree of q root 2i over q, again, this is q root 2 comma I over q root 2i. This also has to be 2 because this is 4 and this is 2, and this degree times this degree has to equal 4. So this one is equal to 2. So that took care of 63. For 65, we want to compute so we want to compute q, again, let's check here, I'm on 65, q root 2 plus root 3 over q, and we want to compute q of root 2 root 3 over q root 2 plus root 3. Okay. So here's the story. This degree is going to be equal to whatever the degree of the minimum polynomial of root 2 plus root 3 over q is. Well, we can sort of go through the same algebra we did before. Alpha is root 2 plus root 3. I want to find a polynomial with rational coefficients of which it's a root. Alpha squared is 2 plus 3 plus 2 root 6, that's 5 plus 2 root 6. Alpha squared minus 5 is 2 root 6. Alpha to the 4th minus 10 alpha squared plus 25 is square this 24. Alpha to the 4th minus 10 alpha squared plus 1 is equal to 0. So if we look at the polynomial, x to the 4th minus 10x squared plus 1, it has root 2 plus root 3 as roots. Right. So this has root 2 plus root 3 as a root. Why is it irreducible? Well, rational root test says it certainly doesn't have any rational roots. In fact, from things we've done before, we can quickly see that the 4 roots of this polynomial are plus or minus root 2 and plus or minus root 3. If this factored into 2 quadratics over q, each of those quadratics would have 2 of these things as roots. Same arguments as before. There's no way you can patch 2 of these things together, x minus 1 of these times x minus second one of these. They're all going to have root 2s or root 3s popping up. In other words, similarly like we did with root 3 or root 5 earlier in the session, this polynomial does not factor into 2 quadratics over q, so therefore this is equal to 4. Now, what about this? Well, here's the story. This is the smallest field that contains the rational numbers and the number of the square root of 2 and the number of the square root of 3. This is the smallest field that contains the rational numbers and the number root 2 plus root 3. Well, notice this field lives inside this field because the square root of 2 plus the square root of 3 both live in here. But this field could be smaller than this field. But now we just take a look at the little picture. Okay. So Q is our tiniest field. And for this particular problems, Q root 2 root 3 is our biggest field. And Q root 2 plus root 3 is somewhere in the middle. And from what we got here is this product, that is, this big degree is equal to 4. Again, you can get that, you can get that this is equal to 4 because when you take Q, throw in the square root of 2, that gets you to degree 2. Throw in the square root of 3, that boosts you up 2 more. So this big degree is equal to 4, but we just showed that this is equal to 4. In fact, we could use the argument that this big has to be at least 4, that this is at most 4, because you tack on 2 things of degree 2, but it contains something of degree 4. There are lots of ways that you can explain this. The point is, this big extension has degree 4, but this tinier extension has degree 4, meaning this times this is equal to 4. In other words, that's equal to 1. So the result that we got is, if you take the rational numbers and throw in these two numbers, you get the same exact field as if you just throw in this one particular number. So again, the fact that this degree is equal to 4 tells you that this degree has to equal 1. So that's number 65. Moving to 67, I think things will be somewhat similar. We want to compute Q root 3 plus I over Q. And we want to compute Q root 3 I over Q root 3 plus I. This should be very similar to the other one. This can sort of reinforce what we just did. This is the smallest field that contains the rational numbers and the particular number root 3 plus I. This is the smallest field that contains the rational numbers and the root 3 and I. So keep in mind, if a field contains root 3 and contains I, it will contain the sum. So this particular element lives in this field, so this field is contained in this field. Now, if we start with Q and we add on the square root of 3, and then we add on I, when you add on the square root of 3 to the rational numbers, you get an extension of degree 2, because root 3 satisfies x squared minus 3, which is irreducible over Q. When you go up from Q root 3 to Q root 3I satisfies x squared plus 1. X squared plus 1 has no roots in Q root 3, because both of these roots are not real, and all these numbers are real. That means this has degree 2, so this has degree 4. So here we have Q. Here we have Q root 3I. Here we have Q root 3 plus I. Again, to keep in mind what this means, this is the smallest field that contains Q and root 3 and I. This is the smallest field that contains Q and the number root 3 plus I. We don't know that this field contains root 3. We don't know that this field contains I. We just know it contains root 3 plus root I, and we showed that this is equal to 4. So, same old situation. Suppose alpha is root 3 plus I. We want to find its minimum polynomial over the reals, or rather over the rationals. Alpha squared is 3 minus 1 plus 2 root 3I. That means alpha squared minus 2 is 2 root 3I. That means alpha to the 4th minus 4 alpha squared plus 4 is, squaring that, I think you get negative 12. Adding 12 to both sides, you get alpha to the 4th minus 4 alpha squared plus 16 is equal to 0. Or root 3 plus I is the root of the polynomial x to the 4th minus 4x squared plus 16. Is this irreducible over Q? Well, we can use the same sort of arguments that the roots of this polynomial are plus or minus root 3 plus or minus I. This has no rational roots, so it doesn't have a degree 1 factor. If this factored into 2 degree 2 factors, notice those quadratics would factor into x minus each of these 4 roots. But whenever you glue 2 of these together, you're going to get a square root of 3 or an I popping up. There's no way to factor this thing into 2 quadratics over the rationals, because again, these quadratics would have these roots, and there's no way that you can patch them together and just get rational coefficients. So the bottom line is this polynomial is irreducible over Q, so this degree is equal to 4. So going to our picture, this big degree is equal to 4, but this little degree is equal to 4. But since this degree times this degree is equal to 4, this degree has to equal 1. In other words, if you throw in the 2 elements, the square root of 3 and I, it turns out you get the same field as if you only plug in the one particular element. So that's number 67. And for 69, something a touch more on the abstract setting. 69 says, suppose you have fields L and K contained in L, and we have an element alpha in L, and we want to show that alpha is algebraic over K if and only if alpha squared is algebraic over K. So let's just take a look at a picture. Let's go for the direction that alpha is algebraic over K. Let's prove this direction. So let's take the field you get from K and throwing in alpha. And since alpha is algebraic, this is some number n. N being the degree of the minimum polynomial of alpha over K. Well, if you think about it, alpha squared lives in here. So K alpha squared lives in here. So this is some number m, which has to be divisor of n. But this says m is the degree of the minimum polynomial of alpha squared over K. So again, if alpha is algebraic, it lives in, this means this field, K alpha, is of degree over K, is degree n over K, where n is the degree of the minimum polynomial of alpha over K. But the field K alpha squared lives in here, because alpha squared lives in here. So that means this degree has to be less than or equal to n. It has to be a divisor of n. So if we call this degree m, then K alpha squared has degree m, meaning m is the degree of the minimum polynomial of alpha squared over K. Well, if alpha squared satisfies a polynomial, that says alpha squared is algebraic over K. So that's one direction. If alpha is algebraic, satisfies a polynomial of degree n, then alpha squared satisfies a polynomial of degree maybe even less. In the other direction, we start with K alpha squared, and then the bigger field is K alpha. Now we're going the direction where alpha squared is algebraic. If alpha squared is algebraic, I'll let t equal degree of the minimum polynomial for alpha squared over K. So this is equal to t. So again, alpha squared is algebraic. It satisfies some minimum polynomial over K of degree t. Now let's go to the bigger field, K alpha. Well, if you think about it, this is a polynomial, x squared minus alpha squared. This is a polynomial with coefficients in here, because alpha squared lives in here. If you plug alpha in here, you get 0. In other words, alpha is a root of a polynomial in here of degree 2. Meaning, this degree is at most 2. At most. So in other words, the degree of K alpha over K, again, the degree of K alpha over alpha squared, since alpha satisfies a polynomial of degree 2, this degree is either 1 or 2. So the degree of K alpha over K is either 1 times t or 2 times t. But what this represents is the degree of the minimum polynomial for alpha over K. So alpha satisfies a polynomial with coefficients in K of either degree t or degree 2t. But the point is, alpha satisfies a polynomial with coefficients in K. I don't really care if the degree is t or 2t, it satisfies something. But that tells me that alpha is algebraic over K. So this says if alpha squared is algebraic over K, meaning alpha squared satisfies a polynomial with degree t, then alpha satisfies a polynomial with degree 2t. In fact, there is an easier way to look at it. If you plug alpha squared into a polynomial, you could see that that's the same as plugging alpha into a different polynomial. But probably one proof is enough. So that takes care of the material on page 590. The final problems that people requested were problems on page 644. So moving to page 644, there's a whole bunch of things that we were looking at here. And in each of these, we want to discuss whether or not they are constructible or not. So let me write them all down here to make it a little easier to read. We get 17 to the 1 over 8, 23 to the 1 over 6, 5 minus 2, 17 to the 1 over 8, 7 plus 9 times 17 to the 1 over 8 over 4 plus the square root of 2. Next page is going to be, come back to these later, next page is going to be 3, 23 to the 1 over 6 divided by square root of 19 minus 2 to the square root of 3. Next one is square root of 7 minus 4 root 3 divided by, I think that's 4 to the 1/3 minus 9. Next is, I think that's 5 to the 1/4 plus the square root of 29 over 4 minus the square root of 5, the whole thing raised to the 1/8. Again, I'll get back to all these. I just want to jot them down. Next one is going to be, I think that's 3 to the 1/4 minus, I think it's 4 to the 1/3 over root 2 plus root 3. Next is 4 to the 1/3 plus 11 to the 1/5. Next is 5 to the 1/4 plus 7 to the 1/8 plus 11 to the 1/16 over 13 to the 1 over 32 plus 5 to the 1/4, and then 2 to the 1/7 minus 19 to the 1 over 11. So, a whole bunch of numbers to check on. And here are the ideas. If you have a number, so in other words, there's a way that you know some things are constructible, there are ways you know that some things are not constructible. If something satisfies an irreducible polynomial and the degree is not 2 to a power, it's not constructible. On the other hand, the constructible numbers are a field containing the rational numbers that also contain the square root of all its positive elements. So, for this particular number, we know 17 is constructible. Therefore, its square root, 17 to the 1/2 is constructible. Therefore, its square root, 17 to the 1/8 is constructible. Therefore, its square root, 17 to the 1/8 is constructible. Maybe I said that wrong, but again, here's the idea. Constructible numbers are a field. They contain the rational numbers, and they contain the positive square root of everything in it. So, 17 is constructible, 17 to the 1/2 is constructible, therefore 17 to the 1/8 is constructible, therefore, I keep calling this, 17 to the 1/2 is constructible, so is 17 to the 1/4, so it's 17 to the 1/8. So that's constructible. 23 to the 1/6, notice that's a root of x to the 6th minus 23. So this gives you a field extension to degree 6. That's not a power of 2. That's not constructible. Next one, 17 to the 1/8 we saw was constructible. Since the set of constructible numbers is a field, If you multiply it by -2, you're still constructible. If you add it to 5, you're still constructible. In other words, this one is constructible. For this one, 17 to the 1/8 we said was constructible. Square root of 2 is constructible. So here you are, you're just adding constructible numbers. You're just adding and multiplying constructible numbers. You're dividing constructible numbers. In other words, as long as you're just combining constructible numbers, the set of constructible numbers is closed under addition, multiplication, et cetera, so this one is also constructible. The key being, since 17 to the 1/8 and the square root of 2 were constructible, both of these are too. Next. The square root of 19 and the square root of 3 look fine, but that 23 to the 1/6 is not constructible. So you can sort of argue this way. If this was constructible, if you multiply by the denominator, which is constructible, you'd still be constructible. In other words, if this number was constructible, the numerator would be. But if this number was constructible, when you divide it by 3, running out of hands here, 23 to the 1/6 would be constructible. In other words, if this is what was constructible, if you multiply out by your constructible denominator, you're still constructible. If you divide by 3, which is constructible, you'd still be constructible. If this number were constructible, so would 23 to the 1/6. So this is not constructible. Same kind of thing here. Taking square roots is fine. This 4 to the 1/3 is sort of a problem. So here's the idea. If this thing were constructible, and since the numerator is constructible, because again, you can construct the square root of 3, so you can construct 7 minus 4, the square root of 3, so you can construct the numerator. If this were constructible, then its reciprocal would be constructible. You could eventually get down to the point of, if this were constructible, then 4 to the 1/3 minus 9 would be constructible. But if 4 to the 1/3 minus 9 was constructible, when you add 9, 4 to the 1/3 would be constructible. In other words, you could argue that if this number were constructible, then 4 to the 1/3 would be constructible. But since 4 to the 1/3 gives you a field extension of degree 3, it's not constructible. Moving on to the next one. Notice what you've done here. 5 is constructible, so is 5 to the 1/2, so is 5 to the 1/4. 29 is constructible, so is the square root of 29. Here you're adding 2 constructible numbers. 5 is constructible, so is the square root of 5. Here you're subtracting 2 constructible numbers. So the numerator is constructible, the denominator is constructible, therefore the quotient is constructible. If you take the square root, or the 4th root, or the 8th root of a constructible number, you still get a constructible number. So lo and behold, this one is constructible. Now, finishing up, root 2 is constructible, root 3 is constructible, 3 to the 1/4 is constructible. So, if this thing were constructible, if you multiply by root 2 plus root 3, you would still be constructible. If this was constructible, if you subtracted away 3 to the 1/4, which is constructible, you'd still be constructible. So the bottom line is, if this number were constructible, then so would 4 to the 1/3. But because 4 to the 1/3 is a root of this polynomial of degree 3, irreducible polynomial of degree 3, you're not constructible. In other words, the reasoning being, if this were constructible, then the numerator would be, since this is, and that would imply that 4 to the 1/3. So this one is not constructible. I may jump over one. Let me make sure that I'm reading it correctly. Okay, let's jump to this one because it's a little bit easier. 5 is constructible, so is 5 to the 1/2, so is 5 to the 1/4. 7 is constructible, so is 7 to the 1/2, 7 to the 1/4, 7 to the 1/8. 11 is constructible, therefore so is 11 to the 1/2, 11 to the 1/4, 11 to the 1/8, 11 to the 1/16. Same reasoning here, 13 to the 1/32 is constructible because you just start with 13 taking square roots. Here all you're doing is you're just adding a bunch of constructible numbers. You're adding a bunch of constructible numbers. You divide, you're still constructible. Take the 4th root, that's like taking a square root twice. everything that you do here keeps you in the set of constructible numbers. The only things left are 4 to the 1/3 plus 11 to the 1/5. Now, this takes a lot of computation, and I won't drive you through all the computations. This thing does not satisfy a polynomial of degree 2 to the n. In fact, if you do a lot of work, it turns out that the minimum polynomial for this thing is actually of degree 15. It takes a lot of work, so I won't go through all the details, and I wouldn't ask you anything this hard, but it turns out this satisfies the polynomial of degree, let's see, did I say, let's see, this is 4 to the 1/3 plus 11 to the 1/5. It turns out that this satisfies a polynomial of degree 15. I won't make you go through all that work. Similarly, 2 to the 1/7 minus 19 to the 1/11. This actually ends up satisfying a polynomial of degree 77. Again, I wouldn't give you something all that hard because I wouldn't expect you to come up with a polynomial of degree 3 or 77. But the point is, these satisfy polynomials of degree where the minimum polynomials are degree not 2 to the n. So these two are not constructible. And I think this takes care of all the questions that you had. So I hope this was helpful. I will put this, well, obviously, if you're watching this, you know that I put this online. But what I will also try to put online will be the sheets that I wrote up. I hope this helped. I hope you have a great weekend. Have a good one. Thank you.